till the end if I'm sort of in the middle of a story.
Sure, definitely.
Yes, so I'll reserve that right. Okay.
Yes, and please repeat the question into the mic.
Yes, okay.
Okay. So.
Yeah, the microphones don't pick up people talking.
No, of course. Yeah.
So, hello and welcome, everyone who's watching from Air Mozilla. My name is Monica Chu, and I work on the security and privacy engineering team here at Mozilla. And today we have a special guest, Ulfar Erlingsson from the Google security team, who's going to talk about macaroons, which are much more delicious than cookies.
Thank you,
All right,
Monica.
thanks.
Okay, so I'll start with a little bit of preamble before I actually get into the talk. And this is sort of to put things in context. In the 90s, soon after public key cryptography was discovered and sort of actually became practical, there were a lot of different efforts to try to use public key crypto in interesting ways to solve authorization problems. And so most of us know the Kerberos system, which really dates back to the 80s, which used symmetric crypto, and it had certain limitations. So there was a big effort in the 90s and throughout until the early aughties of formalizing all of the things you'd want to do with authorization and figure out how to best do that using public key crypto. And the big sort of projects on that were simple PKI, SPKI, Spooky usually, and SDSI, which was a system from Ron Rivest at MIT and Butler Lampson and some others, which was simple distributed security infrastructure. So the intent there was, based on some work that had been done on something called authorization logic, was to figure out what are exactly the public key credentials that we'd like to express things that come up in authorization decisions. Things like, well, I have decided to endow this company with some rights to this particular object, and they can delegate who actually gets to access the object with various permissions to their employees and so on. And so it was actually all quite nicely formalized of what are the things we'd like to do. There were concrete proposals, RFCs and so on in the 90s for how to do this. And in the late 90s and aughties, there was an even sort of larger effort called trust management, stemming really from some work done around AT&T of trying to figure out how do you, in practice, in a company setting, enforce these types of fancy policies using the public key crypto. The short summary of what happened to this work is it all came to naught, and there was a huge compromise, and what we got instead was public key infrastructure as we know it today. It was all deemed way too complicated. Nobody could figure out how to actually get companies to agree on what these public key certificates really looked like, what they meant. So instead, there was a sort of deal with the devil that we're going to have one guy that knows how to assign identities. We're going to trust them a lot because they're going to do a really careful job. And then we're just going to believe those identities. And so what came about because of that is basically HTTPS and the domain name sort of assignment to public keys, and to some extent client certificates, although they never really caught on. So there was a trade-off, basically. Adoptability and simplicity was deemed more important than all of the flexibility of these schemes that people have been talking about. But this was somewhat of an unfortunate compromise because instead of just one guy that's very careful, we have about 400 guys, and they're not necessarily all that careful, and we don't really have a good way of discriminating between statements from one of these guys versus the other. So it's getting to be a pretty long preamble, but basically there are two sort of extremes in how to do authorization. One of them is you have an identity and you do some sort of access control against that identity. The other one is you have a pure bearer token capability. Anybody with that capability can do stuff. If we take a concrete example, imagine you're going to a restaurant and you hand your car keys over to a valet. That's a pure capability. Anybody with that car key can drive the car. The extreme with identities is you ask the valet for their driver's license or some other official identity assigned by some trusted third party. You program your car to accept that identity as a valid driver, maybe for a limited time. And this is basically how ACL-based systems work. You index using an identity into, and there's a middle ground, which was the stuff explored in the 90s, which is credential-based security. And people are still doing academic research on it, but it basically never became real. And the credential-based security says something like, well, even though there's no trusted party to assign identities to people you can program into your car, you can sort of create papers that the car will accept for a limited time, allowing driving the car around 1 mile away from the restaurant, sort of in a confined context, for guys wearing yellow jackets working for that valet company. And so you create this statement, this paper, you give that evidence to the valet in some way that they can present it to the car and drive it. And clearly this has benefits. In particular, it's still something you can carry and is something you give to the valet, but it's much less powerful than the capability, the pure capability. So with that, I'm going to actually show you how we can do all of this fancy stuff using just cookies. And we're going to do it in a special way, so you have many layers in the cookie, and they turn from regular cookies into macaroons. And macaroons and macarons are the same thing if you go and read up on Wikipedia and so on. So I'm showing a picture of macarons. So what are the problems? Well, I don't have to explain to you here that stealing cookies is a real problem, and cookies are these powerful bearer tokens. Cookies are everywhere because they're really simple. So handing your car key to the valet is a really simple act, and cookies are a great way to understand who is visiting your website. As they're coming back, they can have a shopping basket, even though you have no relationship with them. You just know that they're the same guy, just gave this cookie and so on. And you can sort of see how cookies very quickly became a powerful primitive to build the web around. The problem is that they're extremely simple and fragile, and OAuth 2 tokens are really just cookies. So are we really going to build the rest of the world around this simple, fragile thing? In particular, they're easy to steal, and anybody that can carry them can use them, basically. And there is not sort of this notion of confining the cookie so it can only be used in the parking lot here and so on. There just doesn't have a lot of that. Although at Google, we've done some work on sort of origin-bound cookies. Macaroons are basically better cookies that allow you to put arbitrary restrictions on the cookie. And those restrictions can include statements about third parties, like that valet company and its employees should be the ones that are driving the car, which is better than programming the car with one particular driver's license of one valet, because it means that all of the valets in this area can drive the car, and you don't have to wait for one of them to come back. So it's based on cookies, in particular the cookies that have integrity. So usually when we mint cookies, it's really just a random number. But this has the problem that if we want to serve out something under that random number, we have to have a database of all the random numbers we issued out and recognize them. So it's actually easier to avoid having the database, just have one key that we remember at our service. Here we have some sort of service on the internet, which clearly is just going to show pictures of cats, because that's what happens on the internet. And anytime we see this random number with an HMAC computed using the right key, K0, we're going to serve out pictures of cats. And all we have to now remember is K0 instead of having a big database. So whenever this nice young lady, the sister of the main author on the paper we had about macaroons at NDSS, sends this cookie back, you can check the HMAC and say, yep, this is something that I actually crafted, and send back the picture of the cat. Now, the key enabling idea for macaroons is that you can actually do this in layers. You don't have to do this step where you compute an HMAC with a single key once. You can actually have multiple keys involved in a stack. And this gives you great flexibility. So let's imagine for a moment that instead of just the random number, we actually have some key identifier, maybe a shorter number at the beginning, and some statement about what this cookie actually means. And then we have the HMAC at the bottom. So we still have some randomness or some value, and it doesn't have to be necessarily very long. We have a statement about what the cookie is good for, getting the grumpy cat, and then the HMAC value. Now, let's call the actual concrete value, and this is the key trick of Macaroons. It's not very complex. It dates back all the way to the 80s. It was used in the amoeba distributed system. Let's take this value, the concrete yellow number, and call that key 1. And let's use that again as an HMAC key. So we take the output of an HMAC function and use that as the key for an HMAC function. And in our paper and so on, and we can talk about that's actually okay to do with respect to cryptography. So let's take this value away a little bit. Let's take that statement, cat grumpy, and let's add more caveats. So macaroons are cookies with caveats, and what's interesting about them, anybody holding a macaroon can add as many caveats as they want, only valid within this location, only valid for a short time, or whatever you want. And so here we added a caveat, but now it won't be recognized anymore by the service. So we have to put a correct yellow HMAC value underneath. So instead of the original one, we'll actually use the old HMAC value as K1, as the key to compute a new one, based on the thing we appended to the existing cookie. So when that nice young lady has this new token that was somehow attenuated, it was further restricted with an additional caveat about time, and sends that back to the server can look at the key identifier and say, okay, well, what was the original key used to mint this cookie? That's K0. Use that K0 to compute out from that first line, K1. Use K1 to compute out the second line, the caveat, K2, and then simply check that K2 is, in fact, the value found at the very end. And this is HMAC chaining. As I said, this idea has been around for a long time. We use it in a slightly nice way which allows us to involve third parties, but otherwise you can view macaroons as just a careful application of this trick. So if that final green check mark actually works out, you know that this is a valid cookie. You still don't know if the request should be okay. For that, you have to check that has the expiry time passed. Is the request actually requesting the grumpy cat picture? If it's requesting something else, you shouldn't allow it. So these are conditions, these are caveats on this credential. So if those things work out, then in fact, you should send out the grumpy cat. Now these we call first-party caveats because they're really intended for the service that is minting these macaroons. So they can be added by anybody later on. So you can imagine that if, say, your car minted macaroons that allow driving the car, you could add all kinds of caveats before you hand that macaroon over to the valet about, like, how long is this good for? Only tonight, only for within this region around the restaurant, and so on and so forth. The car has to recognize all of those conditions. So there's no constraints. Presumably there's some globally recognized constraints like time and so on, maybe even location. But the car could have all kinds of constraints that are only recognized by that particular brand of car, like don't drive faster than 20 miles an hour, and so on and so forth. So this clearly allows for attenuation, restricting authority. But it also allows for delegation. So let's see how actually delegation would work, not in the case of cars and valets, but like on the web. And well, on the web, because we're in whatever the current web world is called, it's not Web 2.0 anymore, that was a while back. But anyway, so actually you're going to host all of the cat pictures on Amazon. So that's basically how it's going to work out. And Catfolio is going to do almost nothing. And so Amazon is going to be holding the K0 and handing out macaroons for all of these pictures. Those Macaroons are going to basically say, well, Catfolio is, and of course I work for Google, so I should say Google Compute Engine and all of our cloud offerings is how you would do this. Anyway, so you would name this as a valid customer in good standing and have some sort of identifier for the key for that customer, for the K0 key for that customer. And you'd add an HMAC value. But Catfolio would then, with its users, add some constraints about what the different users are doing. Like this particular user is allowed to get the grumpy cat picture maybe for a certain time or something like that. Hand that over to the user, and the user would hand that over back to Amazon. And Amazon can then go through and, just as before, check all of those things actually hold true and show the grumpy cat. So that's delegation. So Amazon handed over the power to access its services, storage services, and to the Catfolio service. Catfolio could then give users access. So in a sense, Catfolio was delegated a region of the disk of Amazon and could further constrain access to that. But so far, all of these limitations are sort of just in one chain, and there's only really the parties in the chain that are involved. And in many cases, we actually want a third-party service to check various assertions. And it's sort of easy to see why third-party services would come up. The easiest thing is a time service. So far, everything we've been talking about is sort of using globally synchronized time. Everybody has the same notion of time, but you might actually want to refer to a time service. And that's not really involved in any of these chains, but its statements about what the time is are actually important to the chain. Similarly, in certificates, in any certificate scheme, you're going to have some sort of revocation service typically. The revocation service might have huge accessibility and scalability and might serve out revocation lists for multiple parties. So you want to sort of involve their statements somehow that things have not yet been revoked in these chains. But we'll see also that group management and any sort of statements about groups or membership in groups and so on actually naturally come out here. So how would third-party caveats play out on this scenario that we're showing before? Well, so far we haven't really talked about how Catfolio recognizes its users. And because this is whatever, Web 3.0, Catfolio doesn't really want to be in the business of recognizing users. They want to delegate that to somebody else. Let's call them Google for now, or maybe it's Facebook or somebody else. So they're going to have some relationship with the parties that they want to delegate user management over to. So let's say that they have a key KGoo for Google, and this might be Google's public key. For now, let's just assume that it's Google Public's key. It comes back in a second. So as before, the storage service would have a key identifier and the name of the customer, Catfolio, and an HMAC value that gets sent over to the Catfolio service. Now, Catfolio wants to forward that. So this delegation, this is complete delegation. Catfolio can do anything it wants with the resources it has at the storage service. Catfolio wants to give limited access to that one file name, not to everybody, but to this fine young lady here. So to one user. So they have to add something that restricts the power to that one user. Now, to do that in Macaroons, you mint out of thin air a new random number, which here is called KC for caveat. So it's a caveat key that you just pick as a random value. And you actually use a holder of key proof of this random value as a way of authenticating the user. So, and here's how you embed the requirement for a holder of key proof into the macaroon. You take this key 2 times and you split apart. One value, the gray stuff, goes to the storage service as before. The other value, the purple stuff, is intended for the third party. And so let's take more closely a look at what's inside this split part here. One side is simply an encryption for the target service so that's the left-hand side, the gray stuff, is an encryption of this new key under a key that you share with the storage service. Now, what key could you possibly share with a storage service? Anybody holding a macaroon actually shares a key with the ultimate recipient. That's the HMAC value. So K2 here is simply the HMAC value, the yellow stuff that was found at the bottom of the macaroon. So you can encrypt a message to the ultimate recipient at any time and put into the macaroon. So that's what you do here. You encrypt this key, this randomly generated key, and say, hey, ultimate recipient, please make sure that you have a proof of this key being involved. And then in the purple bit, you encrypt the key for Google using KGOO and add a caveat that needs to be discharged by Google saying, please make sure that the user is cat lover. And so the purple bit is opaque. Both of these bits are actually opaque to anybody who would look at the macaroon. But in particular, the purple bit is opaque even to the ultimate recipient, even to Amazon. So Amazon doesn't have to know which user was restricted to by the cat folio service. So there's some privacy benefits there. So anyway, so you have this new augmented macaroon with this third-party caveat. And this is really, the third-party caveat business is really the innovation in the macaroon paper. You send that over to the fine young lady. She takes the purple bit and has to do something with it. The entire credential as sent over to the lady is actually useless. It offers no service so far. So it's clear that you have to take this purple bit and get some proof that the purple bit has been discharged, has been sort of fulfilled. That caveat has been fulfilled. And she sends that purple bit over to Google because there's actually in the paper, we have this hint of where could you send this to get a proper proof. And Google can unencrypt and get the fresh minted key, the KC, add any set of first-party caveats. These are messages for the storage service about how long it thinks access should be granted. So in this case, it says, oh, I'm going to say that this is the user, but don't trust me on that for more than 10 seconds. It really just isn't a good idea. I know them. They might log out or something. And they could also, Google could put all kinds of other, and we call them contextual caveats. And this is really what helps with cookie theft in macaroons, or theft of macaroons. It could add requirements about IP addresses. It could add requirements about keys that are present in the web browser at the client or anything else. So basically, this response that comes back can be bound in various ways. One way that's actually in this picture is that this chain that comes back from Google cannot be further extended. So usually the main macaroon, you can add to it at any time, but any of these, we call them discharges. So these third-party caveat discharges, they're sealed. They cannot be tampered with once they're created. You can't add anything to the end. We simply do that by hashing again the value at the bottom. So, and we'll see how that. Anyway, now having gotten this response from Google, the fine young lady can take two credentials. One of them from Catfolio saying she should be allowed to see grumpy cats. The other one from Google saying that, yep, as far as the grumpy cat stuff is concerned, I'm the cat lover at Google. Combine them into a tree or a set of credentials, send them over to the storage service, and the storage service can verify and grant access. So for granting access, as before, you check the signature and the caveats and all of that. For each of the third-party caveats, you have to go through and check all of the statements that are in there. The purple bit is the only thing you assume has already been checked. And as before, the purple bits are actually encrypted, so it's not even necessary for Amazon to know exactly what the check was. So first of all, Amazon or the storage service would check the HMAC value on the main macaroon. Then it would extract out KC, the root key for the discharge. It can do that because as part of computing out K3 here, it gets K2. It's just a key in the chain. And using that KC, it can now verify the discharge macaroon, and it sees that the final value has been hashed twice. Then it goes through and checks all of the first-party caveats that are intended for it to check. And only if all of those turn out to be green, it should grant access. Yes?
Why seal off the discharge macaroon? Why not allow additional constraints to be added by?
So the question was, why seal off the discharge macaroon? Why not add additional constraints? So the short answer is paranoia on our part. We could not really think of very good reasons why you would want to add. Anybody that holds the main macaroon can always add caveats there. And sometimes the things that are added to macaroons might actually amplify rights, because in particular, so it really depends on who is interpreting these things. So even though we give guidance that all of the things get added should always only attenuate rights, maybe they might amplify rights and so on. And for the discharges, the easiest way is that you can't add anything there. So anyway, why would you use macaroons instead of something else? Well, we had those two extremes we talked about at the beginning, the pure capability of the valet getting the car key and the pure identity-based system of you programming your car with the trusted third-party issued driver's license for the valet. In the space of things in the middle, they're very flexible. So all of this credential-based, claims-based, or evidence-based authorization security is very flexible, but it all required, until macaroons, to get the flexibility, you really needed to use public key crypto. So speed is one thing. This is lightweight and fast. It just uses HMACs, so even implemented in JavaScript in the web browser, it's fast. That's not enough, though. So the real reason, as we can tell from the practicality of this, is when you issue a credential, be it an identity credential or some sort of token or something like that, you always have to worry about how long should it last. And so do you issue it for 5 minutes, for an hour, for a day? Like in Gmail, you get a cookie that allows you to access Gmail for several days, like it used to be 21 days, etc. So how long should it last, this credential? With macaroons, because they are so lightweight, we're talking that it costs really just microseconds to get fresh credentials. You can actually make it so that every single request carries a set of fresh credentials that expire immediately. And then we'll get into that. So basically, instead of saying we're going to issue long-lasting credentials and then we're going to always be checking revocation services, you can actually construct macaroons in such a way that you are constantly getting fresh credentials from some service, and that service going away revokes all of your stuff. So that fine young lady that had that capability to see grumpy cats, if Google refuses to give her any more issuance of her being cat lover, then all of those credentials are worthless. So you can immediately revoke them at some granularity. Now, so you have the timeliness, I think, as one of the main advantages, but then there's also simply flexibility. So as with the valet example, it really, often you want the flexibility of being able to designate the conditions under which you should serve content. And I think this is especially acute for like CDNs and other sort of edge services, where you really don't want those edge services to be making all kinds of complex checks and lookups in databases in the back end. But at the same time, they might be serving content for all kinds of different purposes, and some of that content might be private and subject to authorization. So you want basically those authorization checks to have happened already. And then finally, adoptability. We can implement HMACs in JavaScript. We can implement anywhere we have anything remotely looking like a modern computing platform. We can implement macaroons. And this has been one of the main problems with public key-based crypto, is getting all of the algorithms, all of the things into all of the platforms, and then deciding exactly which algorithms are there has been a long-standing battle. So on the timeliness front, because I focused on that, let's sort of look more carefully at this case of identity caveats, the third-party caveats that talk about the identity of somebody like the cat lover lady. Well, Google would presumably give some sort of long-lived credential to a local web browser frame, let's say Gmail or login.google.com, and this frame is living inside the client, be it the mobile device or the web browser, and can answer requests using post message, for instance, in the web or an intent in the mobile space. But basically, Google can give a discharge that lasts for a long time, but from that discharge, you can actually compute out other discharges. So there's a relationship with Google. This relationship can basically depend on that key that's resident in the web browser. So when Catfolio hands over a capability, that capability, the purple bit, can say, I need something from that frame in the user's web browser. And you can get something using post message on the order of microseconds or milliseconds at most from that frame. So you can actually have those credentials that come back last only for a few seconds. And so then those credentials would get sent over to the storage service and you'd get a cat picture. But at any time, if you were to log out or somehow you no longer are a valid user, immediately you would have access denied. You would not be able to pull down those cat pictures. So I said that this was fast, so you can compute that in microseconds. So these are sort of, 2-digit type microseconds or 3-digit type microseconds, or you can sort of talk about how many thousands of these can you do per second implemented in JavaScript. So this is not a high performance implementation in OpenSSL or something. We're talking that you can do between thousands to hundreds of thousands of these in JavaScript, and these are all of the relevant operations. So it's quite reasonable to say that, well, we're going to do this so that the credentials only last for seconds, and then we reuse them within those seconds, but then we just get new credentials because it's really fast and cheap. Now, I'm going to talk again about basically everything. So it's taking a step back. If you lost me at any time or something, I'm just going to reiterate everything, and I'm going to put it in a slightly different spin, which is sort of more in the academic theory of authorization. So what are macaroons? Abstractly, they're a chain that starts with a key at a service. And you can build this chain with predicates, sort of statements, in such a way that you can add statements to the chain, and then given a chain, you can send it back to the service, and the service can check, and you can be basically assured that the service will check all of these statements and make sure that they're true. So you can extend this chain, and the service may grant access, but it will only grant access if all of these statements are true. So this is fundamentally, this is the basic idea of macaroons. Now, you can contextually confine the macaroon. So to prevent it being stolen, you can nail it down to anything that you have that is sort of binding this to a non-stealable. If you have a local key in your web browser, you can say, please make sure that there's a fresh proof using this local key that cannot be stolen because it's in a TPM. If you have an IP address that you don't think is going to change, you can use that. You can use some sort of location proof, whatever you want. So some of these predicates can basically serve to make sure that you have some fresh proof or a property of the accessor that prevents anybody in the world from using this. So everybody in the world from using it. And you can seal it so you can't actually add any more of these predicates. So this sort of is a slightly expanded version of what are macaroons. So you have a different color. Still, it's the service that would check all of these. But you can also have macaroons where there's more than one service that's checking things. So you can take one of these predicates and say, I need a check from this third-party guy. Like a time service would be a typical thing, or something that looks up groups. I want to make sure that this cat lover person is in the, Peninsula Cat Fanciers Association mailing list still, and she hasn't been kicked out for being, too rabidly anti-Siamese. And so this predicate here, the blue one, can basically refer to some other service and say, I demand that there be a valid chain from this other service. And the other service can, when actually providing evidence and a chain, can add any statements it wants that are going to be evaluated by the ultimate recipient, the service. So only the purple bit needs to be established by that third party, but the third party can also add constraints on access evaluated by the first party. More importantly, and this is sort of most important, this is where you get the ultimate flexibility. This is why macaroons are basically equally powerful as SDSI, SPKI, and all of the stuff in the 90s. The predicates in that discharge from the third party. So if the third party is a group management service that says you're in the Cat Fanciers Association, you can add a caveat to a times server or a revocation server or anything you want. And you can be assured that your statement will only be true if there is a proof from that time service. So a third-party time service or something else. So this basically, you can delegate both forward rights and attenuate, and you can also delegate the checking. You can say, well, I think it's okay, but you should also check with this other party. And again, all of this has to be checked before you serve out access. And then this is where it sort of ties in with authorization logic and all of these bits from the 90s. If you take this graph and turn it on its head, it's actually an authorization proof. And we have on the last page of our paper, we have a very simple formalization in a variant of authorization logic that shows exactly how this is. And basically, all you kind of are doing here is you're doing modus ponens, you're doing A, and A implies B. From that, I can infer B if I have those two things. And that's enough to do all of the statements we'd actually be concerned about that need to hold true before the service should grant access. So there's some more fun stuff in the paper. There's some formal verification and definition stuff. There's a variant. You can do all of this using public key-based crypto. It's going to be much slower, but it's going to have one interesting property. At any time, anybody can verify the chains. So it's no longer the case that only the ultimate destination can verify the chains. Probably this is not a super interesting variant. Most likely, if you're going to use public keys in any way, they'd be used to seal up these purple bits to get like, I need a statement from Google, and I don't really have a shared key with Google, but I know it's public key, so I'm going to, make a third-party caveat using the public key. Google can then delegate back to something that's held by its login frame, by an iframe, that is a symmetric key. So the public key operation needs only be done once, really, every 2 hours or every 21 days, and the symmetric key operations can be done on a per-second basis. So there's also comparisons to SPKI SDSI and various other uses of first-party and third-party caveats. So in a short summary, macaroons are fundamentally better than cookies as used in the web today. They're fast. They can be used anywhere, as often as you like, per request. So no longer do you have to sort of worry about creating a credential that lasts for a long time and is usable in many contexts. No, bind it to exactly the context it's being used from and make it last only for a brief period and then send it over. It's flexible. Basically, and in terms of authorization, you can do anything you want in terms of flexibility. It's hard to imagine you'd need anything more in terms of flexibility. And it's also secure. You can prevent the common types of credential thefts, and you can show that the cryptographic constructions and so on actually have the appropriate guarantees. So, any questions?
You said earlier that you have expanded narrowing claims, you have expanding claims. I'm trying to figure out how that works. Because it seems like, it's a matter of evaluation, right?
Yeah. So a question from Eric Riscola. What if those statements in the chains are amplifying rights? That's not a good idea. So we basically advise against that. Every single statement should be limiting, and then you check that all of the statements are true. However, it's kind of interesting that there's also this natural amplification that's happening. If you think of that credential, that macaroon that went over to the nice young lady, it had no power. But as soon as she could go to Google and get that discharge back and combined them, all of a sudden she had power. So there is some sort of built-in notion of amplification there as well. And you can imagine a service like mint.com holding credentials for you, but those credentials are only valid when you actually have an active session from mint.com, at which point mint.com can take sort of a proof from you in your web browser, combine it with all of its things, and go to the various services and get access. And that would then definitely be a case of amplification. That actually makes sense. I'm sorry?
I think actually it's just another form of restriction. It's another caveat, isn't it?
It is another caveat, so you can think of it as a caveat. But if you think of some sort of semantically, you add a statement. So the
statement if the caveat is evaluated as true on the
so yes, the point is being made that actually it's all just attenuation. If you turn it on its head, if you think about like previous solutions that would have allowed mint.com to do what I just described, of actually going out when you are present. So you have some sort of proof of presence, that the user is actually present, which should allow this proxy server to go and access various resources. Usually it's described in terms of amplification. And clearly there is amplification going on in that the proxy server is sometimes not able to do this, but then sometimes it gets some bit that allows it to do all kinds of work. So I don't want to get into, but I agree that the way that we've constructed the credentials, they're all always less power, but then you can combine sets of them and get more power. And so this, I don't know exactly how sets are going to be combined. So in order to make it simpler to reason about that, I'm going to say that only the main macaroon could possibly have new things added to it that have to make me reason about set combinations. All of these discharges and so on don't work that way.
So I just want to clarify though. That makes sense. I want to clarify that, if we have a macaroon and we have a caveat that says it's only valuable on Tuesday, and I have another caveat that's only valuable on Tuesday and Wednesday, it's still only valuable on Tuesday because you're going to value all the credits simultaneously, right?
Yes.
So even though I'm stupid enough to add an expanding caveat, I can never expand past my own security.
Yes. As we and Eric Reskolov just pointed out that as we propose in the paper and as I've described in this talk, all of the caveats have to be true. So if you have a limiting caveat that only allows access on Tuesday, you can add a caveat that says, oh, but throughout the month of January, you're fine. It still only gives you access on Tuesdays. And those Tuesdays might now be in January. Anyway, Monica?
Is this actually implemented?
We have several implementations, and I know of several others that are actually being implemented. None of them have made it out into production use. We had an implementation where we augmented OAuth tokens with this. That was a very, very easy thing to do, very natural. And so for various reasons, so far we haven't sort of made any of this publicly visible, at least. This brings up another question of how would you actually give this power to the world? So with great power comes great responsibility. One of the benefits of macaroons is you can take long documents like the document in OAuth that says sort of usage criteria for OAuth. There's basically a document in an RFC that says, here's actually what you should be doing and all of the checks and so on you should have in your implementation. And you can take macaroons and you can basically say, well, I'm going to issue tokens that require concrete proofs that you did all of those things. So like every time that I actually need somebody to be doing some work, I need them to add a statement basically saying, yes, I did that. And I just put a caveat that all of those statements have to be there, and those can be third-party caveats, so that finally the service will grant access only if those checks were made. But how complex should all of this logic and language and so on be, and how much of it should you allow third-party companies to start working with immediately? Should you limit yourself just to caveats about time, and otherwise these are token, or like at Google, we have channel ID, which binds things to binds cookies to particular keys found in a web browser, or preferably in a hardware token. Should you just say, well, you can only add caveats that bind to a certain place to prevent credential theft? Or is it maybe a short list of things like that? And then later on, you can maybe have, one of the nice things is that the storage service doesn't have to know about most of this stuff. Any of the purple bits, they really don't have to care about. And so similarly, I can create a set of papers using Macaroons for my car, give to a valet, without the car manufacturer having any relationship with the valet service and its notions of, what are proper groups of employees and what subcontractor did they subcontract out to that night. But again, is that flexibility something that you have in the very sort of first implementations and expose completely, or do you actually hide this, hold it as in reserve and saying, well, we now have an insurance policy. We can, using these tokens, which are fast enough and efficient enough, we can do anything. And we're going to start by attacking the biggest problems we have at the moment, like maybe cookie theft and so on, and allow for binding. Like, as you get a credential, you can now bind it to your local machine by basically putting a third-party caveat saying, I need a proof from my machine before I use this credential. Or you can bind the things you send on an HTTP channel. If you ever need to send a credential on an HTTP channel, you can put a caveat saying, oh, this thing I'm about to send only lasts for 2 seconds. So now you limit your exposure dramatically if somebody's snooping on the wire. So maybe those are the things you start with, but you hold the full flexibility and so on in reserve in order to avoid complexity to begin with. Yes?
You mentioned that the third-party constraints have a hint that is intended. Is that intended for the third party to decide what key to use to encrypt some stuff?
No, that's
the end user to figure out which third party to send it to? Does it give the end user any information about what's going to be asked of them when they go to that third party?
Good questions. So 3 questions. I said that there were location hints for the third-party caveats, the purple bits. Those location hints are there just to give you some idea of where you might possibly go to get a valid macaroon that discharges the purple bit. So it's for the user to know where to go. And we explicitly decoupled the location bits as just pure hints. They're actually not integrity checked. So you can rewrite them and so on and send people to various different places and so on. This may sound weird, but there's this premise that in a distributed system, only keys speak. Names are something that your name resolution service can change anyway and redirect you to an arbitrary place. So you really shouldn't be relying on the names for security. You should be relying on the keys. If you need to have a good idea of what will be checked by the purple bits, then instead of encrypting it, you can encrypt it in such a way that the actual caveat is in the clear. So basically, you just add integrity checks and to that, and you sort of put a transparent window on the actual predicate that's being checked. And then the entire purple bit has to have some sort of key identifier. In our construction, it actually serves as the key identifier for the target service to figure out how to decrypt it and actually extract out the root key for the discharge.
So the idea is that the end user sees this purple blob. They know that they have to go to Google to get this discharge. They don't know exactly what will happen or what will be asked of them. But after they give this blob to Google, Google can decrypt it and come back to them and say, oh, by the way, we have to make sure you're logged in. Or whatever the constraint is inside can only be satisfied if you now log into this service.
So the question was, when you get a macaroon with a purple bit, there's a hint that tells you, oh, you should go to Google, and that this purple bit really can be discharged only by Google. You hand the purple bit over to Google, and Google might return immediately and say, oh, I need you to log in. And that's absolutely true. If you're not logged in already, you'll actually need to log in, otherwise Google can't discharge this. If you are already logged in, we've actually, in our implementations, used post message and hidden iframes so that this all happens in the background. There's no UI involved, it just gets discharged. Now, you might worry about that this checking of arbitrary predicates is sort of increasing your privacy risk. And we have a discussion about that in the paper. Basically, we don't think that it actually does. So if some people want to have images that cause you to make RPC requests to various servers embedded in what they send you, they can do that right now, and you will make those requests.
So I wanted to talk about, you said clients can do some things to add additional caveats to something. And that seems like a very useful feature, particularly from the Stephen perspective.
Yes.
What are your plans with respect to actually enabling that? Because these predicates need to be understood by servers, they need to be applied by clients. Who designs the language with which?
So the question is really, there's a comment that it seems useful that users can take their tokens and sort of attenuate them down so that it's harder to steal them. And whenever they use them, maybe they add a final further attenuation saying, oh, the thing that I'm about to hand over the network is only good for a couple of seconds. So all of that seems useful. That was a comment. And then the second question, this is what I was talking about with insurance policy and complexity is, well, what language are you going to talk about? Like, are you going to say that all servers in the world are going to understand this language of all kinds of different checks and so on? And so, no, you would imagine that there would be a very simple initial language that would be globally understood. Anything else, you would have to know that the server you're about to send this to understands that predicate. And there's a simple default that if somebody adds a caveat that is not understood by the final server, the whole thing is invalid. So basically, you default closed. And so this prevents anybody from, you're not going to have the problem that people are adding things left and right that are not really understood by the final servers, because if they try to do that, then these credentials are invalid. And so you'd start off with, I would presume, something like binding to a key that's resident in the web browser, like channel ID, probably the same key, binding time, and some of those simple things that people have used for similar. So all of this is, of course, related to HMAC tokens as used by Amazon and various other companies, including Google, binding to IP addresses or binding to fresh proof, binding to, yeah.
Do you think it'd be useful to have a caveat that binds it to a particular API that's being called, or to a particular set of OAuth scopes that are being invoked at that moment?
So the question was, would it be useful to bind it to an API or OAuth scopes? So for credentials where there is already a notion of different purposes, absolutely yes. I mean, that's the natural thing. And so another way of saying it is, if you have a token that currently gives you access to 5 different aspects of a big popular website, you can do the messaging stuff, you can do the money stuff. And so clearly you would want to be able to tie it down and say, no, this one is just for the video stuff. And like, for instance, if you wanted to hand a macaroon over to a television so that the television can play one of the movies that you, then you would not only want to tie it down to just the video stuff, but presumably only this one movie, and presumably for some limited time and so on. Interestingly, you could throw in a third-party caveat to your own phone device and say, as long as you as the television is on a local network where my phone device is still present, forcing the television to continually get, as long as the television understands this, to continually get sort of fresh proof of present checks from your phone, which I always thought that was a nice little twist. I think we're basically out of time.
Thank you so much. Thank you for the speaker. We're going out to lunch, and anybody Spartan up here, you're welcome to join.
One other question. There's a clip there where the rest of the people are really good.
Oh,
Trying to figure out
thanks.
how to use